Alright, ladies and gents, let's get started. Just fair warning, this video is going to be quite long. I'm going to go through every single question. I'll try to kind of talk through my process, give you some hints on how you can do this in the future, and that's going to take a while. So this video is probably going to be around 30 minutes. Of course, being a video, you can stop, pause, fast forward to go to the pieces you actually need, and you can ignore the pieces that you don't. So let's get to this. Alright, so we're on homework series 1.1. I know the blocks are wrong, just ignore that. Let's jump into question 1. So in question 1, we need to find the value of the unknowns below, and then of course round to 3 decimals if necessary. So in this first question, we have to make some observations, and the first observation we have to make is that we're dealing with a right triangle. Because we're dealing with a right triangle, and we do have 2 of the 3 sides, the Pythagorean theorem will automatically be in play. Please recall the Pythagorean theorem relates to 3 sides of right triangle. In the equation a squared plus b squared equals c squared. And so the job here is really to make sure we know what pieces go where. For some of these pieces, it's not going to matter. So for example, if we look at this side x, it doesn't really matter where we put this as long as we put it on the right side of the equation, or I should say the correct side of the equation. The one that does matter, though, is going to be this side. This side being the hypotenuse, meaning that it's across from the right angle and the largest side of the right triangle. This number 21 has to go in a very particular place, and that's going to be in for C. The logic here is a couple-fold. One, being the largest side of the triangle, and seeing as C is a result of adding 2 numbers together, C also has to be the largest side. And the other piece of logic is that when you look at the Pythagorean theorem, the a squared and the b squared combine to make the c squared, and they have to be shorter in the triangle itself. And so when we're doing a substitution, the c squared has to be 21, so I'll go ahead and input that now. As far as the x, it doesn't matter which for a and b goes in for, it just has to go in 1, which I'll put in for a. Meaning that the last piece, this 8, this side, oh, there it goes, we'll go ahead and put that guy in for b. Okay. Now this is probably where most mistakes get made, to be quite honest. Like if we're not being mindful of what side kind of goes where, 21 usually ends up for a or b, and then you end up with a larger value for x than 21. Keep in mind, since 21 is hypotenuse, that's going to be the largest side, and our work has to reflect that. So now that we have this right triangle, we're using the correct pieces in our equation, our job is now algebraic. We just have to do some simplifying. So x squared will stay x squared, 8 squared is 64, and 21 squared, I'll have to go to a calculator for that. Okay, 21 squared gives us 441. So now we're just in our solving steps. So we need to get x by itself, so we'll accomplish that by subtracting 64 on both sides. Oops, there we go. So 441 subtract off 64, we end up with 377. Okay, so those are gone. X squared equals 377. So let me go ahead and shoot that up here. Our last step here is to get the x by itself, which we'll accomplish by square rooting. And so if I take the square root of 377 in my calculator, I end up with about 19.416. And again, we are going to approximate here to 3 decimals, so there we go. Now, if we want to check this is right, it's an easy thing to do. We just plug this back into the Pythagorean theorem. So if I square 19.416, and then I add it to 8 squared, I should end up with a number, when I square root it, to be 21. And I just did that off camera, I know, but we can confirm that this is indeed the correct answer. It's smaller than 21, which should give us confidence that we're right. And then it also fits within like the a squared plus b squared equals c squared stuff. Okay, so that's that one. Let's drop down to number 2. This is going to be very similar. Again, we can observe that we have a right angle. So we can use Pythagorean theorem immediately. So we have a squared plus b squared equals c squared. Now we just have to input the pieces. Here we have 1 and 1, so this will be 1 squared. Oops. So this will be 1 squared plus 1 squared equals x squared. Again, the only one that matters is the hypotenuse. This x has to go in for c. The other ones have to go in for the sides, whatever order you want. The order doesn't matter, of course, because we are adding together. In our algebra steps, 1 squared is 1, 1 squared is 1, and that equals x squared, which means 2 equals x squared. So in terms of our square rooting, we just had to figure out what the square root of 2 is. And the memory serves is going to be around 1.41. And so we're going to approximate x to be 1.414, of course, with rounding. And again, this fits our model because the hypotenuse has to be the largest number. And although not that much larger, 1.414 is larger than 1, so we're good to go. Okay, so for the second round, we're asked to find the distance of these points. Now, we had a Pythagorean theorem, which actually does find distance, of course. But here we're not afforded a triangle. And of course, we could go, I guess, to a grid and see and go and graph these out and kind of see a triangle. But I think it's just as good to use something like the distance formula. The distance formula is tailor-made to find the distance between 2 points. And all we have to acknowledge is that we do have a couple points here, like point 1 and point 2, which makes this like x1, y1, x2, y2, which is quite convenient for the distance formula, because if you recall, the distance formula, which is just a modified version of the Pythagorean theorem, asks us to take x1 minus x2 and square it, y1 minus y2 and then square it, and then take the square root of the result. And again, you can kind of see those similar steps that we took in the Pythagorean theorem as a distance formula. This one's just more tailor-made to have points as an input. So from this point on, it's just a lot of like plug and chug, as mathematicians like to say. We just got to put the right pieces in the right spots. Okay. So x1 minus x2, well, x1 is here, x2 is here, so this will be 5 minus 2, and we'll square the result. Y1 minus y2 is negative 10, subtract negative 14, and then square the result. Okay. So continuing our algebra, 5 minus 2 is going to be 3. We still have to square it in a second. Recall 2 negatives actually make a positive, and so this would be negative 10 plus 14, and so this would be 4, and we're going to square that in a second. Square root of 3 is 9, square root of 4 is 16, and so that would be square root of 25, which is just the same as 5. Okay. So that's basically the distance formula. I mean, we're just going to apply the formula, pick the right pieces, so let's do that again. Again, we can save ourselves some trouble down the line just by doing some marking here. So that's going to be x1, y1. This will be x2, y2. Okay, so going to the distance formula, we have x1 minus x2, so we have negative 2 for our first x. Subtract the negative 7 for a second. Add that to negative 9, subtract the negative 21, and then squared. Now here we have to be careful with the negatives, but of course, again, we know 2 negatives make a positive, so this is really negative 2 plus 7. So negative 2, sorry about that, negative 2 plus 7 is going to give us 5, and then of course we'll square that here in a moment. Notice I'm keeping parentheses in. This is just good habit, so we don't misenter something into our calculator later. So we have negative 9 plus 21. Just to confirm, we're going to look at 12 here. Okay, so 5 squared will give us 25. 12 squared will be 144. So 144 plus 25 is will give us 169. The square root of 169 is 13. Okay, so looks like we're again just using distance formula for this problem number 3. I'm going to use it, I think, on this one a little modified form. So if we kind of look at x1 minus x2, y1 minus y2 in our original distance formula, when we subtract x values, we subtract y values. All this really does for us is tell us how far apart these things actually are. And so we can probably do that without plugging a lot into a formula. And so sometimes you see the distance formula represented like this. Change in x squared plus change in y squared. And we can probably tell those changes without having to do a calculation. Let me demonstrate what I mean. If my x's go from 0 to 0, the overall change is 0. If my y's go from 9 to negative 10, the overall change here is going to be 19. And so we don't have to, say, use a distance formula in its purest form, as long as we acknowledge that subtraction just finds distance. So here we have 0 squared, which will be 0, 19 squared, which will just be a pretty large number. But if we just have the square root of 19 squared, we can also acknowledge that the square and the square root will actually cancel each other and just leave us with 19, which we could observe right off the bat, because if we have a 0 and then a 0, that means that this will be on the y-axis, and this just goes from negative 9 to 10, which is a total of 19 away. And so we should be cognizant of that too, like we don't always need the formula just because we got it. So it looks like we can find lengths by Pythagorean theorem, we can find lengths by distance formula, and so for this next problem on this set, we need to find the perimeter of this shape. Well, keep in mind the perimeter just means I need to find the total distance all the way around this shape. And so what I'm going to have to find are a bunch of different lengths. We have lots of different ways to do this, and again, we have all these options, especially since we just practiced distance form Pythagorean theorem, and so we have to kind of choose a method here. So one method is we could just use the distance formula. We have the points, we actually have them listed, and so distance formula is definitely going to be a thing for us. But to be quite honest, I think I'm going to use Pythagorean theorem instead. Pythagorean theorem does find the length. We just need a right triangle to do it. And I think we can do that here. Now you could be looking at this and saying, well, there's not a right triangle here to actually use. Well, that just means we have to create one. Geometrically speaking, there's no problem just making a triangle. We know that lines exist at all points in space, all places in space, so we can kind of get them where we want them. And so if I want to find this length, it's just a matter of formulating or creating a right triangle that uses that as, say, a hypotenuse. And I can draw one in here and use it just the same to find this value, which I'm going to label with an x. All we need is the side lengths. Well, we can count those. 3, 4, so that's a length of 4. 3, 4, that's a length of 4 as well. And so finding this length is no different than finding the hypotenuse of this triangle, which we can do below in a second. So what that means is we can just go around the entire triangle and do that. So if I want to find this length, I can just draw on a triangle. 1, 2, 3, 4. Well, look at this. It's actually going to be the same as the one on the left, which is even better news, which means I really just have to find one of these lengths and then double it. I'm dropping down to the purple one. Okay, we have a right triangle. That's going to be 1, 2, 3, 4, 4 by 2. And I bet just by patterning, this is going to be a 4 by 2 triangle as well, which means, again, we don't have to find both of them. So really the plan for us is going to be to use the Pythagorean theorem to find the hypotenuse of the green triangle, do that again to find the hypotenuse of the blue triangle, and then double those to help us find the perimeter. And so really, because we kind of chose this method, we notice this pattern happening, and it's cut our work literally in half. So I'm going to redraw the green triangle here just so I don't have to keep flipping back and forth. So this is a 4, this is a 4, and we're trying to find x. Well, we can drop right into the Pythagorean theorem here. We have a squared plus b squared equals c squared. So that'd be 4 squared plus 4 squared is equal to c squared. 16 plus 16 is equal to c squared. 32 is equal to c squared. And so square rooting both sides. Ooh. Okay, square rooting both sides. We can approximate c to be about 5.65. But since there are two of them, for the overall perimeter, this will contribute 11.314 whatever units it happens to be. Okay, because again, these are going to be the same length, and so we don't have to find it again, we can just double it. Let's do the blue. So again, I'm going to redraw the blue triangle here. This is going to be 2 by 4, and again, we're going to try to find this one. I'll label it the y. But we could drop down immediately into the Pythagorean theorem, which hopefully is becoming repetitive. It's a good strategy to use. It shows up a lot in math all over the place. Y squared. So it'll be 4 plus 16 is equal to y squared. So 20 is equal to y squared. So when we square root 20, we end up with 4.472. And of course, again, this contributes 2 because we're going to double it for the other side because it's a symmetric thing. So this will contribute 8.944. Okay. Now to find our perimeter, we just have to add these two things together. So perimeter is equal to 8.944 plus 11.314. And we end up with approximately 20.258 with rounding. Okay, so the perimeter of this guy is going to be 20.258. Okay, so this will definitely be on the test. Current topics, trying to find using these algebraic techniques to find certain lengths. That's leading us into our next big part of the class, which is going to be talking about proof. We're not quite there yet, but that's where we're going to start right after this next test. Let's drop down to section 2. So this is just some review about notation. It's an important part of geometry. You have to be able to talk and note and identify things well. So let's go to it. We need to sketch each of the following. So the big thing here is that we notice we have this structure. That's a revealing structure. It doesn't have arrows, which means it's finite. And so this is actually just going to be a segment CD. And so we use C and D as the endpoints, and we have this segment. Again, revealing here, we not just have a segment, but we have arrows. And so what this means is we're dealing with a line, and where J and F are just going to be points on that line. So we have to draw arrowheads because, again, it's going to be infinitely long. This is not 3 points. There's 3 points that happen to be working in tandem. And so we not just have like these 3 points that exist in space, but they exist in such a way that they're concurrent on the same plane. So this would be like the equivalent of like taking like a pen and drawing 3 points on your desk. These points all exist on a plane, so ABC represents a plane of some kind. These are all just about identifying context. It's pretty straightforward. It's just recognition. This guy represents perpendicular. Recall perpendicular means things that meet at a 90-degree angle. And so something like this would be appropriate, like for a picture, we have, say, like a line segment AB, and we drop down here to make C. We have that right angle. That's perpendicular, 90 degrees. On the second one, we have parallelism. Okay, so parallelism means that we have two things that are equidistant apart. They never intersect for that reason, and so something like this would be appropriate, where I have this line, which I'll call line M, and then we have this line, which I'm going to call line R. Same distance apart, at least I'm trying to represent it, and the symbol we'd use on the diagram would be these V's. And so we have this notation note for perpendicular that ends up looking like this on the diagram. We have a notation note for parallel, which looks like this on the diagram, these little arrows right there. Last thing we have is congruent. Recall that congruent means things are the same length. And so like on a diagram, if I want to show things are congruent, I use tick marks. And so those are the big 3, I think. So if you're going to be using notation, these come up probably the most. And certainly as we move forward with certain things this semester, we're going to see these more and more. For number 6, we need to sketch a single diagram that follows these rules. So we just have to take it one by one. Again, we have to know notation. So AB represents a line segment. It doesn't give us any restrictions, so we're just going to use AB as the endpoints. Now we have to sketch our defined D, which means we just got to pick a point D, and then we have to sketch AD segment, and so we have to connect whatever point we pick for D, we connect it back to A, and we have some restrictions here. It has to be perpendicular to the original, but not the same length. That's not equal. And so perpendicular means I have to kind of draw it right below it. I draw it below it, so when I connect it, it comes in at a right angle. But they can't be the same length, and so I'm going to mark them differently. One with 1 tick mark, one with 2, meaning that they can't be the same length because tick marks line up and match up to show congruencies. Last thing we need to do is define point C. So we need to pick another point C and then connect it back to B and also over to D with some restrictions. It has to be perpendicular and also has to be parallel to DC. Or AB has to be perpendicular to DC. And so it looks like I probably have to pick this point here for C. We need to sketch BC and DC. It has to happen in such a way that BC is perpendicular to AB, so I can mark it. It looks that way. It's also AB is also parallel to DC, which means I need to mark parallelism this way. Okay, so a bunch of pieces here working together, but in the end, it's just a combination of the pieces of notation and also knowing the orientations. And so if you know those two things, sketches like this should be okay. Let's go on to part 3. Here we need to sketch an example of each shape below. I know we're right in the middle of kind of deciding some of these definitions for sure, but in the meantime, we can kind of use definitions from our memory and also from other resources. Like you can just look up to see what makes sense to be a square. The most common versions of a square that you'll see is that you have a quadrilateral. That quadrilateral is going to need this, and it's also going to need this. Now, this is just a look-upable definition. It's not necessarily the one we'll end up with in class, but it's good enough for now to have that picture in our heads. As far as a rectangle goes, we need that, 4 sides. We do need 4 90-degree angles to make a rectangle. Rhombus. Okay. we end up with 4 sides like that, right? In terms in terms of what these next few terms are, again, I can't expect you to use context clues or simply look them up because they're facts. Equilateral, if you look at the base word equa, meaning equal, lateral meaning sides, we have things that have equal sides, and that's in the end what equilateral actually means. Instead of writing that out, I think I'm just going to draw you a picture here. A good example of an equilateral could be something like an equilateral triangle. Another thing could be maybe something that looks more like a square. As long as all the sides are the same, you have something called equilateral. Using that same kind of logic, equiangular means things with the same angle. So I'm going to draw a rectangle here. Rectangles are equiangular because all the sides are 90. You can also draw something like a regular pentagon, in which all these sides are going to be the same, hence equiangular. Isosceles means 2 of the sides are congruent. We'll still have to argue whether that means at least 2 sides or only 2 sides, but isosceles means 2. So an isosceles triangle would be a good example here, and also maybe an isosceles trapezoid, something like that. So as long as 2 sides are going to be congruent, you can classify the thing as isosceles. Okay. This is not one I'm going to put an answer down for. I just want you to kind of respond to this phrase. It's one that we're dealing currently with in class, but also one that you've heard from your mathematical past. All squares are rectangles, but not all rectangles are sides. Interpret that phrase. You can certainly think about the family tree that we talked about a couple days ago, but that also has something to play into our discussion. But go ahead and put down what response you think is appropriate. I'm not going to judge this one on correctness. I'm just going to judge this one on quality. Let's drop down to our last step, our algebra steps. So just some algebra cleanup. You can expect this to happen all year in an effort to keep your skills sharp for Algebra 2. This is one thing that I noticed we needed some work on, so it's worth answering a few questions about it. We need to round to 3 decimal places, and so like for our first example, if we want to round to 3 decimal places, we do have to look at the one immediately afterwards and ask ourselves a question. If it's 5 or bigger, we round up. If it's 4 or lower, we round down, and round down in this case means keep it the same. Round down does not mean change a decimal, make it smaller. It just means don't change it. And so in this case, since the 3 is not 5 or bigger, we keep it just as it is. And so this will be 3.459. Okay, so that will be the rounding for that one. Same deal. We want to round to the 3rd decimal. We have to look at the one right next to it. In this case, 5 is big enough to bump that one up. So this will be negative 10.1. 9 in this case now 5 because 5 rounds up to 4. Same deal. We want to round to 3. Look at 4. So this will be 7.787 because 6 is large enough to bump that up one value. Look at that guy. We want to round to 3. Look at the 4th. This one is going to cause something called a chain round because 9 is big enough to bump up the next number. But that number is 9, it then in turn bumps up the one right after it. And so we'll end up with 0.010. And since we are rounding to 3, we need to represent the 3rd decimal, even if that is a 0. It works in a similar way in science in terms of like significant numbers. You can think of it in the same kind of realm here. Number 11 asks you to find the slope. And so this might just be a sight recognition thing. And so certainly you can calculate slope, but if you're given an equation in y equals mx plus b form as you are here, we can just notice that the slope, is a number, the coefficient in front of x, and so is 4. And so this one, the slope in this case, just equals 4. Please recall m is a short notation for slope. This is actually an equation in form. Like I guess you could, if you wanted to, get this into y equals mx plus b form. But this is actually a good equation form. This is y minus y1 equals m times the quantity x minus x1. This is something called point slope form if you recall from Algebra 1. And again, the m is the thing, the slope is the thing located in front of the x parentheses. And so if you know this form, if you remember this form, what that tells you is the slope in this case is just negative 2 over 3. All right. For number 3, this one's actually one we're going to have to calculate. Not a big deal. We just have to keep a couple things in mind. One is that slopes are always read left to right. All graphs are, and all we have to do is try to figure out the rise and the run. Recall, a reasonable way to look at slope is going to be what we call rise over run. It's also going to be the same as change in y over change in x. And so we have to bring in our infinite slope triangles. To do that, we just need to pick a couple nice points on our grid. Those points are going to be at nice crossing grid lines. And so we can actually create a triangle here where we can calculate
change in y over change in x. So to go from one point to the next, we're going to have to drop 2. So our change in y, ooh, why is that recording? Okay, so our change in y is going to be the same as dropping 2, so that's minus 2. Our run, in this case, is going to be over 1, 2, 3, 4. So our change in x is going to be plus 4. So in terms of recording that down here, we have negative 2 over 4. And since we can recognize this as a reducible fraction, we can say it's the same thing as negative 1/2. And we do want to keep it as a fraction. Ultimately, that's the better of the two forms to have. Last question, we got to do a little algebra solving here. Not a big deal. You guys have been solving equations for quite a while, so it might be a little bit rusty, but certainly within the realm of what we can do. Remember, to solve means to get x by itself, and so we probably have to do a little cleanup first on each side, because I see some parentheses which triggers distribution. So we have negative 2 times x will be a negative 2x. Negative 2 times 6 will be minus 12. On the right-hand side, we're distributing a half, so making everything half as big. Half of 4x is 2x, half of 4 is 2, positive 2, so plus 2. Now from here we have to start moving our x's around. Recall that the general rule is you keep the larger of the two x's, which would be this 2x, so we have to get rid of the minus 2x on the left. We get rid of minus anything by adding, so we'll add 2x here, and of course we'll add 2x over here as well. Those will cancel to 0, because of course if you take negative 2x and you add 2x, you end up with 0. We'll bring this guy down as a minus 12. 2x plus 2x makes 4x. Bring down the plus 2. Now we're continuing. We need to strip away things on the right-hand side, so we'll get rid of this plus 2 by subtracting it. Move it on the left. Negative 12 minus 2 gives us negative 14, and we're left with a 4x on the right. We're almost done. We just need to get rid of this times 4. We divide by 4 to get rid of a times anything. And so our x value will be the same thing as, well, I don't know what's negative. It's going to be a 4. Sorry about that. So those cancel to 1, leaving an x. On the left-hand side, we have negative 14 divided by 4, which we probably could just leave it as a fraction, but since I got a calculator handy, maybe. Negative 14 divided by 4 is the same thing as negative 3.5, and that's what we'll leave it at for our value for x. For part B, this is just function notation with substitution. So we have this function, we're going to call it f, that uses x, and the way it uses x is that it takes x, multiplies it by 2, and then subtracts 10. And so now we're pondering what happens if we change this x value to a 2. I'm getting that from the last part of the statement. So the function now called f uses 2, and the way it will use it is to take that x value, change it to a 2, multiply it by 2, and then subtract 10. 2 times 2 gives us 4, and then we'll subtract 10 from that. 4 minus 10 gives us negative 6, so f of 2, is equal to negative 6. And so that's just going to be a little bit of plug and chug there for us. On the last one, even though it's a square, we're not going to change what we're going to do. We're still going to get x by itself. We still have to get rid of this times 2 in front, so let's divide by 2. The 2's cancel to make 1. So we have x squared is equal to 36. 72 divided by 2 is 36. So if we square root and we square root, the x value in this case will be whatever the square root of 36 is. So recall 36 just means one number times itself is 36, and that will certainly be 6, but if you leave it at that, you're only providing half the answers, because it is true that 6 times 6 is 36, but it's also equally true that negative 6 times negative 6 is positive 36, because two negatives make a positive. So the proper way to represent your answer would be both plus and minus 6. All right. So that completes homework number 1. Again, I know that video was long, but there was a lot to cover, and so there's 2 more videos coming. But again, you can kind of use this to kind of predict what's going to be on the test. So certainly I'm going to ask you to use Pythagorean theorem and distance to find distances. Sometimes that will be in the context of finding perimeters, and sometimes it won't be. I'll want you to use notation, both be able to sketch notation by the way it looks, understand some orientations like parallel, perpendicular, and congruent, and then put that together to maybe create a sketch. In terms of shapes, we should certainly be able to kind of recognize and reproduce some of the shapes. I know we're still working on definitions, official definitions in class, but there are some things like equilateral, equiangular, and isosceles that are universal. So those definitions are something we can apply right away. And then we have a hint at maybe we're looking at some relationships. Right? Finally, I'm going to ask you to make sure you know some algebra, specifically how to round some values that we need rounding, find slopes in different ways, and of course recall some Math 8 Algebra 1 that you guys have done in previous years. Okay, so that's what I have for you guys for right now. Thank you very much, and I'll see you guys in the next video.